let's talk about the regression benefits of test-driven development. Typically, when we work with a large application, what can go wrong? Usually, it's a question of what wouldn't go wrong, isn't it? Well, when it comes to applications, software systems grow in size over time. As months and years pass by, we keep adding code. Developers come in, they go. Same developers working on the product sometimes happens, but they can't remember all the details all the time as well. But one thing we can say for sure about software systems grow in complexity and they evolve. So when we have a program and assuming everything works fine so far, we come in and add a feature, fix a bug, make an enhancement, whatever that could be. Well, what happens now? How do we know that whatever worked before continues to work moving forward? We could bring a lot of different testers and programmers and bodies and say, go test this stuff. We could run manual tests. But as the complexity and the size of the application grows, it becomes almost impossible to run all these tests manually. So what do? We test a few things, a few critical things, things that are very commonly used. And then what do? We wait. And the nail-biting time begins. And eventually, we hear reports. We get errors from testers. And a lot of times we get errors from the field, from the customers, from the users. How embarrassing when that happens. Now, if you really think about it, what goes wrong in software projects? Well, our expectation of the code changes over time, but when those expectations change, there are other parts of the code that has a certain expectation. Also, software is a nonlinear system. A change here could break potentially something over here. We deal with data structures. We step out of bounds. We got a data coming in. Sometimes the data is different than what we expected, and suddenly we have a null pointer exception blowing on our face. A lot of different things go wrong. So the number of permutation and combination becomes enormous, and often we are not able to deal with that complexity when we write code, and even so, we are not able to deal with all the permutation combination when it comes to testing the software. So what can we do about it? Well, the problem is this. It really is about feedback. When we modify a piece of code, and if something is wrong in the change we made, when do we know that something went wrong? We could get to know that in the next couple of minutes. It could be a day, it could be weeks, it could be months, sometimes years before we find out something went wrong. What if you find a problem in a piece of code 3 years after it's been written? That happens quite often, isn't it? Well, the developer who wrote the code may not be around, may have moved on. And even if the developer is still around, it's very rare that the developer will remember the details, all the details to the right extent. So when a bug is found, an error is found years or even months or weeks from the time the code is modified, the cost is enormous. The amount of money it takes to fix a problem, find and fix a problem, is in proportion to the time between the time the problem is found and the code was modified. If you find the problem soon enough after you write it, immediately you can fix the problem. The developer has everything in their head and it can quickly fix the problem. But if you find the problem a day later, maybe not that bad. A week later, we got trouble already. A month or two later, it's going to be really hard for two reasons. One, you got to take time away from what you're working to go fix that problem. That means you're not able to make progress in what you're working on. It's a showstopper. You got to stop what you're doing and go fix the other problem. That's one problem. The second problem is you got to context switch. You got to load up in your mind all the details of that code. If it depends on the person. For me, a couple of days later, I completely forget all the details about what the code did. And when I look at the code, it looks pretty strange. Sometimes you're like, did I write this even? So you got to load up the context in your head. That takes a certain amount of time, sometimes a few minutes, sometimes hours, sometimes even days, because the complexity of the code is so much, or the application domain and the application itself is so much, we can't remember all the details. And once we load up all the context, we are able to find out what the problem is. But for that, we got to set up the test environment. We probably have to give some sample data, try to understand why things are failing in this context. A lot of these things can take a lot of time and effort. But once we do find and fix the problem, the time has been spent solving that problem, fixing that error. And then, of course, we wonder where else the code is broken and we don't even know it. And then we wait until the next error pops up, and sometimes the same piece of code manifests itself in so many different problems, and we keep fixing the problem over and over. It's even worse sometimes because we fix the problem, then we come back to make more changes, and then it again blows up on our face months later because that change introduced a sequence of other changes and breaking expectations in the code. So to us, when it comes to developing software, the feedback loop is extremely critical. The sooner we know that something is wrong in the code we touched, the better it is, the easier it is, less costly it is, and less time consuming it is. So given all of these, feedback loop is extremely critical. I'll share with you an experience related to this. I was teaching a course on test-driven development in the industry, and right in the front row there were two gentlemen. One gentleman was somewhat proud in admitting to this problem. He said the person sitting next to him, they both share a cubicle, so they literally sit a few feet away from each other. And apparently the first gentleman had modified some piece of code, and the second gentleman found about its effect, and it took him about 2 months to find it. He said he went on to find out what a problem was. There was a problem in a certain output that was being displayed. It was a very critical output in this particular simulator, and he started debugging it. And it was really hard for him to find what the problem is. And after spending days and days and days trying to debug, and eventually he comes to a small part of the code where a particular change to the code had made this change ripple through the system. Then he looks in the version control to see who made that change, and it turns out that it was his colleague who is a few feet away from him, and he had made this change 2 months ago. And it took him a long time to find this problem and fix it. But why is that? Well, this particular change in code violated certain expectation in the code, but there was no double checking mechanism to say, aha, but you violated this expectation, you better go back and check it. When you don't have that kind of feedback loop in the code, the only way you know something is broken is when some particular execution of the code, potentially by a user, runs into that scenario with the sample set of data and configuration and environment, and then boom, it explodes on your face, and you're trying to find out what the problem is. If you're very lucky, the problem you face is very clear, it fails clearly and loudly, but a lot of times things don't fail that way. They fail very quietly, they give a wrong result, and that gets passed on around through the system, and eventually you find the problem somewhere else manifesting in an incorrect data, and now you're trying to go through and debug and trace back where the problem actually originated. This can be very frustrating, very time consuming, not very cost effective at all. While this is all happening, probably users are waiting for us to fix the problem, and there are other pressures on us while we are trying to find and fix this problem. So we want to definitely eliminate these problems by having a good feedback loop. So to understand this, I'm going to create a very trivial example. This is extremely trivial, but I hope this example, being as trivial as this, will nevertheless illustrate the benefit of doing this. If you can get some benefit out of this even in a trivial situation like this, imagine what we're going to get out of this in real hard problems we normally solve. So let's start with a little example. It's an example of a simple calculator. That's pretty much as trivial as that is. So here is a calculator test that I have, and I also have a calculator class which doesn't have anything right now. So I'm going to go ahead and write a first test over here. And so let's go ahead and create a test, and I'm going to call add two positive numbers, let's say over here, returns their sum. How about that? So that is basically the first test I'm going to write. Well, I'm going to use JUnit here, and I've written this as a test, and so I need to call the calculator to do the work. So I'm going to say assert equals over here. Let's say 6 comma calculator.add, and I'm going to say 2 and 4. Extremely simple, as you can see. That's what I'm going to add. Let's bring in a few things we need over here. Let's bring in the assert equals method. That's a static import I brought in. What about the calculator itself? I'm going to define a field for the calculator. So we'll say calculator right there. So we created that calculator object. Now we need to initialize that reference, obviously. So let's go ahead and write a before, and let's go ahead and say here is our method, which is the setup method we're going to create. and it says calculator equals new calculator. Well, that leaves us with this method add we need. Let's go ahead and implement the add method. And I'm going to say this is operand 1 and operand 2. And I'm going to just take return 0 for now. Let's work with that. So when I run this code now, you can see that the test is failing. It tells us that it expects a 6, but the result was a 0. And so we can see that the problem was just that. Well, let's go ahead and fix that problem. So to fix the problem, obviously here, I could simply return a 6 because that's what the code is expecting. So we could simply go ahead and run that and see what it does. And sure enough, we can see that the test is passing. Let's write one more test over here. So the next test I want to write here is called add a positive and negative number returns. And what is it going to return? Again, their sum, right? So that's what it is. It returns their sum. So once again, I'll say assert equals, and let's say 3 over here, calculator dot add, and I'm going to say, well, positive and negative number. So I'm going to say 6 and minus 3 over here. Well, let's go ahead and run the code this time, and you can see that the test actually is failing in this case, sorry. And of course, 3 and 6, because we are expecting 3, we faked a value of 6. So let's go ahead and do the real work, op1 plus op2. And of course, when we can come back and run the test now, we can see that in this case, the test is passing. So that was pretty trivial, wasn't it? Let's do a couple of more things. Rather than continuing with the add, let's go ahead and write a method called for divide. So divide of two positive numbers returns, what does it return in this case? Well, it returns the result of the division, right? So returns the result of division, right? So returns a positive result, let's say. And so that's basically what we're going to do, divide two positive values. So how am I going to do this? So I'm going to say assert equals, let's say again 6 comma calculator dot divide, and I'm going to ask it to do a divide on the calculator. So calculator, there we go. And I'm going to divide over here. Well, I'm expecting a result of 6. I'm going to divide 12 over 2. Let's go ahead and write the divide method to see what it provides for us. So here is the divide method. And again, I'm going to take a numerator over here. And this is going to be the denominator. How about that? And now I'm going to simply return, in this case, the value of 6. That's all I care to return right now. So now let's go back and run the test, and you can see the test is passing. Well, how about one more test over here? So divide of a positive number by a negative number returns negative result. How about that? So that's basically what we are writing here, returns a negative result. So to make this work, we are going to specify, let's fix the typo here, result. There we go. So let's go ahead and implement that code. So I'm going to say assert equals, let's say a minus 3 over here, and calculator dot divide, and I'm going to divide a positive number by a negative number. So let's go ahead and say, in this case, I've got a 12 and a minus 4. Well, let's go ahead and run this code. It tells us that test is failing. We expected a minus 3. It was returning a 6. Let's go ahead and fix it again. So numerator divided by the denominator is what we want to return from here. So let's go ahead and run the test again, and you can see the test is passing. Now, if you were to run a code coverage on this code, you're going to get 100% code coverage. So just because you get 100% code coverage doesn't mean you got all the tests you need. In fact, in this case, we need one test, which is for a division by 0. So let's say over here, the test we want to write is divide by 0. Well, what do you want the code to do when you divide by 0? Well, that depends on what your expectations are. Most of the time, the answer I would hear is, well, when you divide by 0, I want to see an exception. So we could say divide by 0 throws an exception, right? Now, that's basically what we're going to write over here. So how do we go about implementing that? Well, we're going to say over here, try, and we will implement a catch block exception, EX, And here within the exception, if we got an exception, life is good. So we'll say assert true, and we will simply say true, or you can put a little smiley to say everything was good. Now, what exception are we really expecting? I don't want to paint this with a broad brush and ask for exception, so we could say arithmetic exception, which is what I'm going to really expect when you divide by 0. So now I'm going to say assert true. Let's go ahead and provide the assert true method over here. So that's a static import as well for the assert true. Now, what about code within here? We're going to say in here something along the lines of calculator.divide, and let's say 6 over 0. But what if this code throws an exception? If it throws the arithmetic exception, we will land here. If it throws some other exception, we will not land in this catch block. Instead, we would jump out of the catch block, out of the try, and the test will fail because it encountered an exception that has not been handled over here. But the question is, what happens if we don't throw any exception at all? Well, we don't want this to quietly finish this, move on to execute the next empty line, and then cross over the catch and move on and pass. We want to say that if the code does not throw an exception, we want the test to fail. This is an exception test. So the test passes if the code fails, the test fails if the code passes. So to ensure that happens, we're going to say fail over here, and the call here says expected exception for division by 0. So clearly in this case, we are saying that we are expecting this kind of exception. And if this exception was not thrown, then it'll hit the fail method. I call the fail method the landmine method. You step on it, it blows up. And so the test will fail if that exception was not being thrown by the code. Well, let's go ahead and run the test to see what's going to happen. So when we run the test, yay, look at that. The test passed. That tells us that the divide was throwing an exception for us. Well, that's great. So now the question is, was it worth all this effort? The point really is, this test, the purpose of this test is, we have clearly established an expectation in the code. And the expectation is, if there is a division by 0, we are expecting an exception. But imagine for a minute, we do not have any of these test cases because we are not doing any test-driven development, let's say. So I'm going to remove all these test cases. I'm just commenting them out. So no more test cases. Let's go ahead and run this, and you can see in this particular case, I've just exercised it. It doesn't give us any errors at this point. There is nothing to complain about it. So let's go ahead and run this, and you can see that it doesn't complain, doesn't have anything to say right now. Well, that's great. I could also write, just as an example here, one test just to make sure things are actually working. So let's go ahead and say test over here, test run, and let's say assert over here, assert true, and let's go ahead and say assert true is true. And let's just go ahead and run this one more time and make sure it's working. It says 1 of 1 done, right? But technically we don't have any test cases. Now let's say we don't have any test at all, but this is part of a fairly big application. Let's say Joe has written some code doing some really powerful computations. I call Joe's code. Well, Joe then internally, while performing these computations, calls Bob's code. Well, Bob's code is doing some other serious computations, and eventually Bob's code calls that particular function, which is the divide function. Well, Bob's code says, if this code throws an exception, I will handle it and deal with it. If it doesn't, I'll just pass the result to Joe's code. Well, Joe's code calls Bob's code. Bob's code, of course, is interacting with this code. And once Joe gets the result from Bob's code, Joe calls another function, and it goes through a series of computations to do some work, which is doing some other very critical computations. Everything works fine. One afternoon, a Wednesday afternoon, we walk along, and we want to make a very small refactoring. And the refactoring is very genuinely benign. We simply say double. After all, we want to modify these as doubles. So we modify all these 3 as doubles. That's all we did. Now, what's the next thing we would do after this little refactoring? We don't want integers anymore. We want double. Well, obviously, we would compile the code to make sure everything compiles fine. So we can certainly do that as well. Let's run through the compilation to make sure everything is fine. And what would the compiler tell us? Well, the compiler tells us that everything is wonderful. And since we didn't have any test at all, there wouldn't be any test to run. There's no feedback after all, isn't it? But what's going to happen? Maybe a day or two goes by, maybe a week goes by, somebody is doing some manual testing and suddenly something goes poof in smoke. And immediately we're like, oh, wait a minute, something went wrong. We try to dig into the code where it failed, and we find that it failed in Joe's code. Well, we are ready to complain to Joe, and we say, Joe, your code failed. And Joe says, I just came back from vacation after 2 weeks. What did I do? I've not even touched the code base yet. How could I already fail? Well, we try to debug through it, and eventually we find out that the problem started when Bob was talking to this code, and the person who wrote this code had made a little minor refactoring. But what happened because of this refactoring? What could possibly go wrong? Well, to understand that, let's put back integers over here, just like the way we had a minute ago. Let's also go back here and put the tests back that we had. Now that we are into this discipline of writing tests along with the code, how wonderful that is. So let's go ahead and run this code. Notice all the tests are passing. Now let's go back in that weird Wednesday afternoon and we change this to double, change this to double, and change this to double also. So we basically changed these types to double. That's all we did. Now let's get back here to the code, and you can see that test is already complaining a little bit to us, saying, hey, over here in the assign equals, you need to be a little careful. What's the problem? Well, it says that you're calling a deprecated version because it makes no sense to compare two double values head on. You always want to give a delta of how much you are willing to tolerate. So here is the delta that we are providing. And let's define this delta as a field in the class. And we will say this delta, a final double delta is 0.001, let's say. Well, that's great so far. We gave a delta value for that. Likewise, we will also provide a delta value here also over for this one. And while at it, let's fix this little error it's complaining about, positive. There we go. So all that looks great, isn't it? So now let's go ahead and run the test cases and see what happens. Notice that that 1-of-1 test worked fine. Not a problem, isn't it? Well, that's great. But let's run all the tests to see what's going to happen. Oh, wait a second. We have a failure being reported right here. What seems to be the problem? Well, if you notice, the error says expected exception for division by 0, and it's complaining that the code is failing. And where is the code really failing? Well, it tells us the code failed right there at that line number being displayed. That landmine method I talked about was encountered. So what's really happening over here? Well, it turns out that when we had the code like a minute ago, let's go ahead and try this one more time. Let's go back to this code and change all of these to integer values. So these three are int, as you can see. Now when I go back and run all the tests, all the tests that we have so far, when we run it, all the tests are passing. You can see 5 out of 5 tests running. But if I come back and change these to double values instead of integer over here, the story is very different. Notice the test is failing with the double values. Well, obviously the compiler did not complain. The compiler was quite happy. But what went really wrong here? Well, it turns out while integer division throws division by 0 exception or arithmetic exception, floating point division does not throw such exception. That came to me as a shock, actually. I discovered this while working on an application. And this seems to be true across multiple different languages. Java, C++, C#, Ruby, and several other languages. While integer division throws an exception, floating point division returns a nan or a not a number. So the point really is that we don't get exceptions. That is a clear breach of expectation in the code. And so if you can have a violation or departure from expectations in code like this, would you want to know about this problem right away, or do you want to discover this when it really blows up months later? Well, in this case, of course, what's the fix? The first problem solution is to know that there's a problem. Now that we know there's a problem, we could either come over here and throw an exception specifically if the denominator is 0, for example. So we could say if the denominator is equal to 0, then we could say, for example, and of course you may want to say that it is actually a delta that you're really looking for in terms of the difference. So you could say if it is less than, for example, 0.00001 or whatever that may make sense. And then you could say throw new run, in this case, arithmetic exception. We could say division by 0, right? We could solve it that way. Now, if we come back and run the test, you can see that all the tests are, well, actually, division by 0, arithmetic exception. Let's make sure that I'm throwing the right exception at the right place. So it's, in this case, it's complaining that if the denominator is less than that value, let's see what the error says in this particular case. It gave us an arithmetic exception, but that came from a division of positive number by a negative number, of course, because the value is really negative. See how we can get a feedback very quickly? This appears like a good idea, but I was not thinking through, isn't it? So of course the fix there is to say math.absolute value of the denominator is less than. Now I can go. So notice how these errors are, you just saw there how quick that feedback loop was to tell us. Well, that's one way to fix the problem here. Or there could be a compiler setting, depending on the language you are using, that says throw exception for floating point arithmetic division as well. And you could turn on the compiler setting. And if somebody comes along and removes the compiler setting, the test will fail right away. That's again a very quick feedback loop. So the point really is we get the benefit of regression through these short feedback loops. So in a sense, when you're writing code, the test cases are useful to set up a expectation on the code. You would not want to build a refinery with no backup units. You would not want to send a cop without a backup, for example. You would not want to fly in an airplane where there are no backup devices and engines, for example. In the case of programming, the test is your backup. The test is telling you, here is the code, here's the expectation of the code, I'm going to ensure that code behaves the way I expected. Anytime the code deviates from that expectation, you get a very quick feedback loop. So that shows us, this example shows us how regression benefit comes from test-driven development. The other benefit of TDD, of course, is the design benefit, and we will see that in another presentation. So you can see how by using enough automated tests, we can get these kinds of regression. What if you do find a bug? You should never convince yourselves or anybody that using TDD guarantees no bugs. That's a myth. That's not true. There will always be bugs. But what TDD gives us the ability is to make sure the bugs don't recur in the code. So when you have enough test cases and the code, everything is working, you find a bug, what do? Don't fix the bug. Write a test first so the test fails because of the bug that is there. Once the test is failing, then fix the code and ensure that the test is passing. And once you do that, you can make sure that if a similar bug were to arise in the same place, that test will be there to guard you and protect you. So write tests and let those serve as a guard for your code. And if you find bugs, write more tests so that those bugs don't recur in the code, and we can benefit from TDD through these regression benefits, and that gives us a quick feedback loop, improves confidence in our code, and it makes us look like really good programmers who can develop reliable and robust software, which is really what we are really trying to do, is to provide really cost-effective development, develop relevant software, take feedback and quickly get back with changes, and when you do evolve based on the feedback, those tests tell you that your code is still working. When I was writing an application, I am a person who visualizes these things quite a bit. And I said to myself, this is amazing. The code I modified immediately failed a number of test cases. So I immediately told myself, this is pretty amazing how these tests are helping me. I mean, you would definitely agree to this. You would much rather have your code tell you your code sucks than your colleague tells you your code sucks. Well, these test code can immediately give you that feedback cycle. So I was thinking about this and I said to myself, oh, these appear like angels on my shoulder. They sit there and whisper in my ears, hey, Venkat, that change really sucks. Don't check it in. So I was thinking about this and I wrote one of the sections in the book I was writing. I wrote it as tests are angels on your shoulder. Well, Dave Thomas, the publisher of my book, Practices of an Agile Developer, said, Venkat, if you have angels, do you also talk to devils? Well, I said, well, I seem to talk to devils more often than angels. And the next day he sends me a photo of a programmer sitting and coding with a devil and angel on the sides of the programmer's ears. And that's what eventually became the cover of the book, Practice of an Agile Developer. So this is something that I really enjoy doing in terms of writing these test cases, because I feel these tests are the angels on our shoulder. They watch over us and they whisper in our ears when things are beginning to fall apart. They serve as a very quick feedback loop. So definitely benefit from those test angels if you can.